Well, it's our last lesson. All right. And we are going to be doing inference for slope. So that means it's our last statistic, joke, comic, whatever. So let's go ahead and look at a regression. Basically, amount of statistics geekiness versus the desire to make a graph representing a linear relationship. So if you are looking forward to this lesson, join me in the geekiness. All right. Speaking of geekiness, I was like looking at that Harvard admissions lawsuit data, and I remember hearing the story. Oh, well, there's some correlation between SAT and income. And I thought, and I was like, that's interesting. So what do? I go around scouring the Texas, because we have Texas report cards, and you can look up the percent of students that are economically disadvantaged and their average SAT score for the school. And I went ahead and gathered all these districts. I basically did a cluster sample. So I said, okay, now I did include our district because that was for you. Admittedly, that wasn't random, but we're going to pretend it's good enough, that it's representative, okay? So I have Alamo Heights, Azle, El Paso. So once I got that one, I already had a lot of my cluster right there. Leander, PSJA, and actually I threw in one other one. Here's my high school. 51.7% economically disadvantaged, so they would be roughly around here. And the average SAT score at Rio Hondo was a 953. So I'm guessing they're about there. Okay. So, yes, that's where I went to school. Now, where do you go to school? You go to school at Cedar Ridge. 29.2% economically disadvantaged. And so that's about here. And I think that's about a 1061. So, somewhere around here. One of the, probably that dot. So you can see there you are. There I came from. So, hey, at least you got a leg up. At least you're over in this area, right? So we're going to go ahead and write down and interpret the equation of the line for the least squares regression. Remember, you need to be able to read it from computer outputs. Odds are they're not going to give you a list of data to put in a calculator. They're probably going to give you a computer output, and you will see one on your AP test, I promise you. So where do we find the slope again? Well, hopefully you remember from our prior lessons that it is the number right there under coefficient, and it's always the second number, and it has a variable next to it. So that's your slope. All right, and then your y-offset, or your y-intercept, is right there. It's called the constant. So the way we write it is we have the hat. Why do we have the hat? Because that's not the actual value, it's the predicted value, okay? Is negative 3.451 times the percent of economically disadvantaged students plus 1234.2. You'll say, hey, that's high. Well, it's because we have negative slope. As we go, it decreases. In fact, that's how we interpret it. For every 1% increase in the percent of economically disadvantaged students, the expected mean SAT score decreases by negative 3.451 points. So how do we describe the shape and the relationship? Well, it is definitely linear. And the way I'm going to take it is the computer outputs don't give you R. So you have to go ahead and calculate it. And see, this is R squared. So I take the square root. But you notice I have a negative sign in front. Why? Because it's a negative slope. This R squared always loses the sign. So you have to make sure that you put the correct sign there when you're calculating it. So we have actually a strong relationship, negative 0.88 for the relationship between the percent of economically disadvantaged students and average SAT. Now, some of you might be going, but there's a lot of scatter there. That should be moderate. Actually, that's pretty strong. That's considered strong right there. Okay, so linear and strong. What percent of variability is explained by the model? Well, that's where that R squared comes into play again. About 77.44% of the variability. And honestly, is it exactly that? Probably not. And mean SAT scores is accounted for by the linear regression model. Okay, so that's kind of a review of what we've done so far. And the other thing we always need to do, and we've done this before, is we use a dot plot of the residual. So what I did is I just went ahead and put my data into Statlet, and created the dot plot, and there's no obvious pattern in the residuals, right? It looks a little tight there and there, but that's at the ends, you know. It's like, no, not too much. The spread's pretty even, all right? And the linear model is appropriate. So as we go across, the spread doesn't change drastically. So we say, yeah, we can use a linear model for this. So now we're going to examine regression some more. So I'm going to actually start by looking at a regression for a population. So I'm intrigued. I pull this data and it's like, interesting. So I found this study called Race, Poverty, and SAT Scores. The title's actually a little longer, keeping tight on the room, by Dixon, Roman, McCardle, and Everson. And they look at all of the results for 2003. And the thing is, students will actually self-report their income bracket frequently when they take the SAT. And just to minimize ethnicity as a confounding variable, all right, because I just want to look at income and SAT score, I went ahead and took the scores for the white students, all right? They also had, the study actually looks at both Black and white students. It looks at them separately and it looks at them combined. Okay, so we're going to write down and interpret the equation of the line for the least square regression. Again, remember your slope is right there. So that's what we multiply the income by. By the way, the income is in thousands. So I'm not going to put 50,000. I would just put 50. The constant is 474.36. So it sounds like even if you have no money, we would expect a mean score of 474, right? So the SAT score, the expected SAT score is 0.7355 times family income plus 464.36, all right? And the way we would interpret that, for every $1,000 increase in family income, the expected mean math SAT score, and says expected, increases by 0.7355 points. Now we want you to predict the mean math SAT score for a white student with a family income of 50,000, right? Because remember, our model's for white students. So here's our model, right? And we're going to take that 50,000, and we're just putting 50 in it because it's already in thousands. And we get 501.1. All right, so remember, this is just math SAT scores. So if you think 501 seems low, it's because it's just the math. They also have data on reading as well, so that might be interesting to look at. Do you expect the student to make exactly this score? Note the population is approximately normally distributed with a math SAT score standard deviation of 103 for white students. So since they had the whole population, I actually have sigma, which is nice. All right. So we expect a normal distribution with a mean of 501.1 and standard deviation of 103. So I went ahead on Stafflet and I got the normal distribution for that. So you can see there they are. Note that this only applies to incomes of $50,000. Each family income will have its own distribution, but it should be the same standard deviation roughly, just it's going to be shifted based on family income. So what's the probability that the student makes higher than a 600? Well, hopefully pretty good. Basically, we find out our test statistic, right, 0.960. Notice I'm not dividing by sample size here because I'm just looking at one individual. If you wanted to divide by sample size is 1, right? Square root of 1 is 1. There you go. All right. So 600 is what we're testing, the value. And 501.1 is our parameter. Well, yeah, our estimated parameter. And 103 is our standard deviation. All right. So we just basically do the probability that it's greater than 0.96 or 0.168. Now, you could also just keep this model in the Stafflet and say greater than 600, and it would be right there. And you can see that's about 16.8% of the curve, which makes sense because it's roughly 1 standard deviation above. Okay. So let's revisit the sample we did. So if we were to look at schools with the same percentage of economically disadvantaged students, we don't expect every school to have the same mean SAT score. We would expect some variation along a normal distribution with a mean close to where the regression line passes. Remember, I said we have a model for every value of X. In this case, our values of X are the percent of economically disadvantaged students. So when we look at the model summary, we see something called S for right there, 58.23, and that's estimating sigma. It's the standard deviation of the residuals, all right, the residuals. So if we were to interpret S for this regression, the way we interpret it is that the actual mean SAT score for each school is typically about 58 points away from the number. It varies up to 58 points away from the number predicted by the, actually, it is about 58.023. It can be more from the number predicted by the least squares regression line. Okay, so when we create a regression line for a sample, maybe if I had gotten different schools, do I expect to get a different slope? Sure. I don't know if I got the true slope. So here's what we're going to do. We're going to look at a simulation right here, Rossman Chance. It's a very cool simulation, all right? So what I have here is actually input all the data that I gathered from the SAT and plotted the, here's the scatter plot right here. You can show, now they let you actually on this applet, you can have a movable line. So if you wanted to, you could show the residuals. There we go. Show the residuals when you play with this line. So if you were trying to figure out how that works, and you could even show the squared residuals, right? Playing with your movable line. But we've already done that. So let's go ahead and actually show the regression line. So this is the calculated least squares regression line, right? And I can show the residuals on that if I wanted to, and the squared residuals, right? And the whole point of the regression line is that we are minimizing the sum of these squared residuals. It provides us the best fit. And the correlation that we're seeing, now you're seeing a lot of scatter here. Correlation is still quite strong. It's negative 0.880. So that falls into the strong category. And we can see there's a 77.4% that we already showed you. Okay. And the regression output here, you can see that's kind of like the computer output that you do need to be able to read. So there's our slope and our intercept. Okay. So what are we going to do now? Well, we're going to pretend, what if this data just happens to be lining up, right? So I'm going to do a simulation and say, oh, let me go ahead and scramble the y values. I'm going to keep the same x values, but I'm going to scramble the y and see what kind of line I get from that. So let's go ahead and scramble it once. And you say, oh, look at that. Slope's positive on that one, right? So you can see it right there. Where is it? Yeah, 1.14. Okay. I could scramble again. And what will happen is every time I scramble, you see I have slopes ranging. There's a -1, there's a positive slope. But let's go ahead and scramble it a lot. Okay, so I'm going to scramble it 100,000 times. Okay, and so if I were to scramble, it's going to take a sec. There we go. So these are all the possible values, well, not possible values, but all the sample simulated values that we've done when doing this by random chance. As you can see, my slope is outside of that range, all right? And what was our actual slope? Our actual slope is negative 3.45, right? So it should be, it's over here somewhere. Well, I can actually count the samples less than, say, -3, all right? How many do we get there? None. Okay, just for the fun of it, -2. How many do we get there? 43. So we got 43 out of 100,000 for simulations, or about 0.04%. So this is just kind of looking at things, creating a sampling distribution for slope. So we're introducing you to that idea. Why? Well, the underlying part of our hypothesis test and our confidence intervals have been based on sampling distributions. You've seen them for proportions. You've seen them for means. Now you can also do it for slopes. And by the way, look at this. You can also do it for correlation. So let me go ahead and let's see. Yeah, here's showing the correlations. So if I have a correlation, obviously I'm not going to have 0, but say less than -0.5, right? So it will count samples with correlations, and our correlation actually was -0.88. So you could infer correlations as well, but that's currently outside of the scope of this lesson, but that doesn't mean it couldn't be an investigative task. So correlations are similar to slopes, right? In fact, we have a formula that relates them. So what we saw is based on the simulation, what is the probability of getting a slope as extreme as -2 just by chance based on this output? It is only 43. We had 43 out of 100. Oh, I got 1 0 missing. There's a 0 missing. Out of 100,004, or basically 0.004. So now that brings us to inference for slope. All right. This is on your math chart under inference for slope. Your variable is b, our parameter is beta, and then here's our sigma for slope. So we have a standard deviation for slope, and that's our standard error based on a sample. And you can say where sigma of x, and you can calculate those on the statlet, and s is your residuals, and s of x is your basically your standard deviation for your x value. So let's go ahead and now notice something here. If you look at this formula, do you see the standard deviation of y and the standard deviation of x? So this one's on the front of your math chart, right? So sigma b, it's sort of keeping that same relationship, right? Except we don't have the r in there. So, and because we're doing sample size, we are dividing by square root of n. So there's a relationship between these two. Now let's go back to our example with our students, right? What is the parameter for slope again? It is beta. Mu sub b is beta. Not to be confused with power. I know, it's so annoying. So many similar symbols and names. Our statistic is b, all right? Now, you might see a b0 and a b1, but basically that's what it is. All right, and we get it from the computer printout. That's our estimate for our sample, okay? Our y-intercept is alpha. Isn't that the same as type 1 error? So annoying. Okay. By the way, maybe that's why sometimes, like on older stuff, you might see a B1 and B2 or something. But on your calculators, it actually tends to be A. They tend to do A and B on your calculators. In our example, our A is up there, right? So the regression line is mu sub y. Notice there's no hat because it's like the true regression line, equals beta x plus alpha. Okay. And in our sample, so what we're normally writing, because we don't normally know that, we're normally writing y hat equals a plus bx. Although I tend to put the bx first, but anyways, as you can see. So there's the SAT equals, and that's in the order they put it in. Okay, standard deviation of x is sigma of x, and that's s of x. Now, you're not going to get standard deviation for x from the computer output. So if you had a list of data, or if they gave you the summary statistics, I went ahead and put the data in the statlet, and you can see my standard deviation is 31.632. So I happen to know that. Oh, that's not what I meant to do. Then for the residuals, that's sigma, all right? And it's the sample statistic is S. So that means you can find it right there. And in this case, it's the 58.0325. Then finally, standard deviation for slope. How do we calculate that? It is this beautiful formula that's on your math chart that I just showed you. And it actually goes through a change for the sample. It is S over S of x divided by square root of n minus 1, right? And that should have been on your formula chart. Are you going to have to calculate this? Probably not. Probably not. But basically, it's on your formula chart. You would have to have that S of x if you had to calculate it. I happen to have my S of x, and I have my 58.025, and my sample size was 40, so minus 1. So 0.29845 is the value I get. Oh, wait, it's right there. So you don't normally have to calculate it. It's on the output. So how do we interpret this number? If we took repeated samples many times, the slope of the least squares regression line would typically vary by about 0.298 from the slope of the true regression line for predicting mean score. Okay, so that's how. So all of these they vary by typically these amounts from, in this case, from the true mean of x, this one from the true mean residual, from the true mean predicted value, right? And this one would be from the true mean slope, or the true slope. I don't need to put means on those. All right. So so if we're checking conditions for inference, yes, we do have to check conditions. Basically, it's easy to remember an acronym, which is LINER, or you could say linear, where A is optional, like line and R regression. It's helpful to remember the conditions. So the first regression, the first L stands for linear. Yeah, it looks roughly linear. So we're good there. The data should be independent. So that means that one school should not be affecting another school. Now, that might be interesting in a cluster sample. That could be an issue. Like El Paso just has one ISD, so maybe not so independent. Don't know. All right. Check a graph of the residuals. So N, we're trying to check basically that it looks fine, right? That it's not too skewed, no outliers and no strong skew. And this looks fine. Equal spread. So we need, the spread should be roughly the same for both large and small values, right? And this does look very roughly the same. You could say, well, those two, yeah, but it's not that big a deal. It's just like over here. It's not like it was a fan, like a funnel shape, right? Where it's clearly some sort of difference. This one's like, well, maybe if I had more points, I might have some down here. The data should come from a random sample or randomized experiment. So the random condition holds here, just like with everything else, okay? So again, don't freak out. You're like, whoa, that looks skewed. Yeah, it's a little skewed, but it's not super strong. You have to really be breaking laws over here to say, oh, we can't do inference. Now, you can always say, we'll proceed with caution. That's always allowed. So what are our hypothesis tests? So our null hypothesis is that there is no correlation between the variables. Kind of like our chi-squared for independence, there's no association. So, except we use the word correlation when talking about regression. All right. And by the way, correlation does imply association, but it's between two quantitative variables. All right. And then we're saying, so that means you're probably thinking, wait a second, we're saying it equals 0. Yeah, it's because if it's 0, that means it's just scattered, right? And then our alternate hypothesis is that it's not 0. We say there is a correlation. So that might feel a little weird. You got to know there and an equals there, and you got to not equals there, and it's just there is. By the way, on your computer outputs, p-values are always two-sided because the computers are always testing this set of hypotheses, all right? And we usually, so here's the formula for the test statistic from your math chart, but in this case, it's going to change a little bit. We usually assume the parameter here is 0 for no correlation, but we could actually test for other correlations. So we're allowed to put other values in there, but most of the time, you're just going to be testing against 0. So our test statistic is B from our sample minus beta. In this case, we're testing against 0. And our standard deviation for the slope is S of EB. And remember, you can get that from the computer output. It's right next to the slope under SE. And then now this is another twist too. Instead of subtracting 1 for degrees of freedom, we're subtracting 2 for degrees of freedom. The way I always think about it is, can you do the calculation? You'll always need 1 extra than or what you need to do the calculation. So if you're calculating an average, in theory, you could do an average of 1 point. So for just averages, you need 1 extra, right? So you have your 1 is your base, so you go n minus 1. For slope, you need at least 2 points to calculate slope. So that means you got to subtract those 2 points and you're just counting the extra. So for me, degrees of freedom always feels like what you have is extra. Okay, so in our example, we're going to test the hypothesis that so we actually have a previous example when I did the conditions. The stats teacher took a random sample of 27 students and recorded their GPA and the hours they reported playing video games, all right? And so our state is that the slope is 0 the true slope is 0, but we're going to test if it's not, right? So we're saying there's no relationship here, but here we're saying, oh, maybe there is. So where beta is the true slope of the population regression line relating GPA and hours playing video games. Plan, we're going to do a t-test for the slope of a regression line. So we're going to check, is it linear? Yeah, this is pretty much linear, right? Is it independent? Well, he did 27 students, so we need at least 270 students in the school, assuming that was his sampling frame, right? And it's probably pretty reasonable to assume that. N is normal. We do not see any outliers or strong skew. For some reason, I was thinking this was the SAT data on the previous slide, right? So we're good there. And equal standard deviation, the residual plot shows similar scatter with slightly less variation at lower hours. All right, so, and that's, I mean, again, that's not too bad. Random, the 27 students in the data set were randomly sampled. So we're good there. Now we're going to be able to get most parts of our the calculation, straight from the printouts. But let me go ahead and show you where the things are coming from. All right, so there's our coefficient for, that's our standard error for the coefficient. All right, so that's 0.185, the standard error for our slope. And there's our actual slope, B, that's our sample estimate. Notice how I have sample notation on these. And then I can calculate the test statistic. It is negative 0.678 minus 0, which is our hypothesized slope, divided by 0.185, and I get negative 3.66. Oh, it's right there. I don't technically have to calculate it. Now, do be careful on the p-value, all right? So first of all, I need my degrees of freedom. 27 minus 2 is 25. And our p-value, remember, it's two-sided, so I have to double this, make sure I go in the right direction here. Negative infinity to negative 3.66. For you guys, it would be negative 1 e to the 99 if you're on a calculator. And our degrees of freedom is 4. So we get 0.0012. Oh, that's on the printout too. Then, so we would report our test statistic and our p-value. Personally, I think it doesn't hurt to report your degrees of freedom. And because this is conclude, because our p-value 0.001 is less than our alpha level at 0.05, we reject H0. We have convincing evidence of a linear relationship between hours playing video games and GPA. Now, could you be tested on direction? Yes. In fact, your assignment sometimes will ask you that it's more negative, or that it's a negative slope, or that it's a positive slope. So this would be testing just if the slope is positive. This is testing for a negative relationship. So what do we do there? Well, that's just a one-sided test, all right? So we're just going P, the probability our test statistic is less than negative 3.66, and we get 0.00059. Now, you could just take that p-value and divide it by 2. That would work as well. All right. Now, the way we calculate confidence intervals for slope is very similar to the way that we've done the other confidence intervals. It's the same formula on the math chart: statistic plus or minus critical value times standard error for the statistic. Your part is they'll have that on the chart, but they won't have the specifics. So you need to remember the statistic is B, the critical value is T star, all right? And the standard error is that SE of B, which is on your formula chart, or you can pull it from the computer printout if they give you one. Degrees of freedom is N minus 2. And so we're going to go ahead and do the interval for our example. We still do the state. We are estimating beta at 90% confidence, where beta is the true slope of the population regression line relating hours of video game play and GPA. The plan is pretty much the same, except we've already done it, so I'm going to skip that part. And then the do. So we need to calculate our critical value. Do not use the T that you see up here. That's the test statistic, all right? Just want to be clear. And then so we substitute in our B. There's our test statistic. And then we have our standard error, 0.185 from there. And I get an interval of negative 0.994 to negative 0.362. Then finally, there's the conclude, which is we are 90% confident the interval from 0.994 to negative 0.362 captures the true regression slope for the linear model relating hours playing video games and GPA. So one last thing to think about, it's if we this is our standard error for our estimate on our slope, right? So if we want tighter intervals, we know that minimizing that error, lowering it, will give us tighter intervals and more powerful tests without having to change our confidence level or alpha. All right. So, how can we lower that SEB? We can lower it by increasing the spread in the x direction. So you can see here what I did is I took these dots and then the same number of dots in both plots, and I just moved some of them further out, right? I'm trying to simulate roughly. So you feel more confident in your slope on this one than you would on that one. And the reason is it increases S of x because now you have more variation in the x direction. That's actually a good thing. And that's in the denominator, so it lowers it. The other thing we can always do, increase sample size, right? So always think increasing sample size, unless you're breaking the 10% condition, it's a good thing. Or we could decrease the spread in the y direction, but honestly, I don't know how you do that. But if you do see, like this is tighter, right? Increased spread usually has a negative impact when it's in the vertical direction. So you don't want to increase S if you're trying to improve this, and understand how that impacts it. So increased spread in the y direction, bad for SEB. Decreased spread, good. And that's it for our lesson. We're done. Crazy.